Let's have a look at page 1, right, of your regular worksheet, circular motion and gravitational field. Okay, so this is June 15 P41. Let me just open it up. So this is a very common definition question, asking you to define Newton's law of gravitation. You can just say that the gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. Okay, the important part is only this. The next part, they say, provided that the separation is much larger than the size of the masses, this side is actually not really required. You don't need to write this. You just follow strictly what's inside the notes, you should be fine. So there are 2 marks given here for this definition. Now, the first mark is usually for you mentioning point masses. This is where 1 point always comes from. And then the next point where you say is proportional to the product of the masses and inversely proportional to the square of the separation, this is where the other point comes from. All right. So whenever you define Newton's law of gravitation, please remember to always write point mass. This is the key word in the law. Point masses only. Okay. Right. So this one you can just slowly copy it from your notes later on. All right. Now let's go through B. Now for B, they tell you planet Neptune has 8 moons or satellites. Each moon orbits Neptune in a circular path or radius r with period t. Assuming that Neptune and each moon behave as point masses, show that r and t are related by this expression gmn equals to 4 pi square r cubed over t squared, where g is the gravitational constant and mn is the mass of Neptune. Okay, now this one, usually when you look at the gravitational field questions and you notice that there's a square term and a cube term, usually you would know that it's relating to Kepler's third law. Okay, all right, because in your entire chapter, this is the only equation that has a square and a cube term inside. All right, when you see a square and a cube term inside whatever equation that you need to prove, usually it almost always will tie back to Kepler's third law, okay, and how to derive it. So here they're asking you to kind of derive Kepler's third law in another different form. Okay, so here they basically mention this to you. Wait, let me just get out some stuff. They tell you that this is Neptune, and then they tell you that you have moon that orbits around it in circular orbit. So you can say that the Neptune has mass m and the moon has mass small m now. Okay, so they're orbiting at a they're orbiting at a radius of r with a period of t. So you want to derive out the equation. The first thing normally you can say is this: gravitational force provides the centripetal force that allows your moon to move in a circle in the first place. Okay, now I would suggest that every time you want to write, before you want to write the equation Fg equals to Fc, always write this statement first. When you write out the statement specifically saying that gravitational force provides the centripetal force, because this statement sometimes is where your mark comes from. You have 3 marks here. The first mark actually came from you writing that statement. Okay, yeah, we know that gravitational force is equals to centripetal force. If you just write this first without writing this statement, you won't get your full marks. Okay, so for some reason you have to write this statement out before you proceed with your equation. All right, so just remember that. So gravitational force provides your centripetal force. Fg is equals to Fc. So you can just use Fg equals Fc gmm over r square is equals to mr omega square to derive. The only thing you need to be careful about is that your big M is now mn. Okay, so you try and write it out. you get gmnm over r square equals to mr omega square. And then what you do is that you substitute out omega to become 2 pi over t. All right. Then from there, you just proceed with your derivation. Eventually, you get gmn equals to 4 pi square r cubed over t square. All right. This is the derivation part for Kepler's third law. Okay. So this is all right. Okay. So if this one is fine, the derivation is fine, then you move on to part C. Okay. So let's move on to part C. Now, data for moon Triton that orbits Neptune and moon Oberon that orbits Uranus are given in figure 1.1. So you have two different planets with their respective moons, and then you are given the radius and period for each case. So from here, they tell you, use the expression in B that you just derived to determine the ratio of mass of Neptune to mass of Uranus. Okay, so the case here is that you have Neptune with the moon Triton, and the moon Triton, and then you have another different moon, different planet, Uranus, plus the moon Oberon. Okay, so you have two different pairs of planet and their moons. Okay, now in the case for Triton orbiting around Neptune, and in the case of Oberon orbiting around Uranus, the same equation actually applies to both cases. You can actually say that for both cases, Fg is equals to Fc, which in turn will give you t square over r cubed equals to 4 pi square over gm. Eventually, like this is Kepler's third law. All right. So what you want to do is that you are trying to find the ratio of the masses, right? You make use of this equation, Kepler's third law, for both cases, because this is the common equation that links both cases together. So something similar to your ratio method that you learn in AS, you try to find out what is the common variable here first. Okay, so in your cases now, your equation derived was actually gm equals to 4 pi square r cubed over t square, all right? But it's still the same form as this, all right? Now, what is common to both cases? The only thing that is common to both cases is the universal gravitational constant G, as well as 4 pi square. The big mass M is different for both. The R, the radius of orbit is different for both. The period of orbit is also different for both. Okay, so there are no other constants other than G and 4 pi square. So if G and 4 pi square are constant, you can then say that M is proportional to R cubed over T square. Okay, so from here, you can actually then work out these values here, where you say that Mn to Mu is Rn cubed over Tn squared over Ru cubed over Tn squared. So eventually you get this, sorry, Tu, my mistake. Okay, so eventually you're going to get Mn to Mu, Rn to Ru cubed, Tu to Tn squared. So those values of radius and period, you already have them from the previous part of your question. Sorry, from the previous page. You know the period, you know the radius. Okay, now you may be thinking right now that this one is in kilometer, and then this one is in days. shouldn't you convert this to meter and shouldn't you convert this to second? Now, here you don't need to bother because you see, you are taking those values as ratios. You are going to have the units cancelling each other off. So for the radius, it will be kilometer to kilometer. And then for the period, it will be days to days. So the unit actually cancels off. Even if you will change to meter, they still cancel off. Or you were to change to second, they will still cancel off. So there's no need to do any conversion. You can just use the value straight, knowing that the units cancel each other off. Okay, so just take the ratio. Remember to cube for the first set, and then remember to square for the second set. Eventually, you get your answer as 1.18. Just like that. All right. This is one part. Okay, so this is all right. Okay, there's actually a more complicated method where you find out individually the mass of Neptune and mass of Uranus, but that one will be a lot more complicated and a lot more tedious because you have to do your conversions of your units where you convert from kilometer to meter and then days to second. Okay, so this one not really recommended because here you see just now you had gm equals to 4 pi squared r cubed over t squared, right? M can be 4 pi squared r cubed t squared over g. So you apply this individually for Neptune and Uranus, you should be able to get the individual masses, the exact values. And then after that, you have to do the ratio again. So this is actually a bit more tedious. Okay, this one is not something that is recommended. All right. Okay, have a look at page 7. This is November 15, P43. Okay, now state Newton's law of gravitation. This one is the same question that we just did just now. You can just copy the definition from your notes, all right? The definitions don't change. The marks that are allocated to it are always the same, all right? So gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. This is the only important thing. Provided that the separation is much larger than the size of the masses, this is not important. Don't need to bother. Okay, so that one is all right. Okay, then after that, you look at part B. Part B is somewhat similar again to what you've just done, but this time they're describing a different situation now. Some of the planets in solar system have several moons that have circular orbits about the planet. The planet and each of its moon may be considered to be point masses. Show that the radius x of a moon's orbit is related to the period t of the orbit by this expression. Okay, so again, you see got a square term and a cube term. This one you know should be relating back to your Kepler's third law and how it's derived. So here you can actually say that if you have a planet with mass capital M and its moon with small m that's orbiting around it, your radius is x, your period is t, you would just have to say that gravitational force provides the centripetal force. Now, in your gravitational field questions, the moment you see explain your working, this one here, this one almost always relates to this. The explaining your working part is telling you you need to write this. Gravitational force provides your centripetal force. That's where what explain your working here means. Okay, the moment you see the term explain your working, it's actually asking you to write this statement. Gravitational force provides your centripetal force. This is where 1 mark comes from. All right. So the rest of it is just your derivation again, where you say Fg is equals to Fc. So you just say that GMM over R square is MR omega square from Fg equals to Fc. The only thing you need to be careful of here is this, your R is actually your X now, okay? Your orbital radius is not defined as R in your question, it's defined as X. So you just change the variables accordingly to X. Okay, so it's GMM over X squared equals to MX omega square. Substitute for omega, you're going to get 2 pi over T. And then eventually this answer here. Okay, GM is 4 pi square X cubed over T square. Alright, so this is basically the same thing as what we've just done. Okay, the next page will be slightly different than what we've done. Okay, now if you have a look at that, they're telling you right now, planet Neptune has 8 moons, each with circular orbit of radius x and period t. The variation with t squared of x cubed of some of the moons is as shown in figure 1.1. Use figure 1.1 and the expression in B to determine the mass of Neptune. Okay, so you have a planet called Neptune, and there are about 8 moons that orbit around Neptune. So say this one is Neptune now, and you have 8 moons that orbit around it, all at different radius, at different periods. Okay, there are 8 of them. Okay, but all 8 of them are moving in circular orbit around your planet, around Neptune itself. Okay, so since all of them are moving in circular orbit, you know you can say this one, Fg is equals to Fc. Eventually, T squared over R cubed is 4 pi square over Gm. All right. Now here, they want you to find the mass of Neptune. They're actually asking you to find the value of big M here. Okay. But here they give you a graph. So what you want to do is you try to relate that equation to your graph. Basically, you try to relate what you just derived, which is this form, to the graph. So just now we told you that you just now derived that Gm is 4 pi square x cubed over t square. You look at your graph right now, this one is x cubed, this one is t square. You try to rearrange it such that it forms a straight line equation. So this one will be x cubed Gm over 4 pi square x cubed. All right, so this one is y equals to mx plus c, where y-axis is x cubed. Okay, wait, sorry, I think I did this thing wrong. This one is t squared, right? This one is t squared. All right, and then here you will get x-axis as t squared. Your gradient is going to be Gm over 4 pi squared. Okay, so to find your M, the mass of Neptune, you just need to find the gradient. Okay, so gradient is Gm over 4 pi squared. Right, so all you just need to do is to find the gradient. And then after that, equate it to Gm over 4 pi squared. You know the value of G, you know the value of 4 pi squared, so you can actually find out the value of M. Okay, but here you need to be careful a bit, because what you're given here, the units are not in meter nor are they in second. You see this one here is in kilometer cube, this one is in day square. So when you do your gradient calculation, you need to be careful to change them to meter cube and second square accordingly. So I can actually say that 1 kilometer cube is 1 kilometer like this in bracket by cube. So this one becomes 10 power 3 meter cube. It becomes 10 power 9 meter cube. And then when you're talking about 1 day square, it's the same as 1 day inside a bracket square. Then this one becomes 24 hours, 60 minutes times 60 seconds square. Okay, so this is your conversion. So here, what you just need to do, pick 2 points from the graph. It could be this point and this point. Find the gradient equated to 4 pi, equated to gm over 4 pi squared. The working is like this. All right. Okay. Gm over 4 pi squared is gradient of the graph. Find the gradient. Remember to do your conversion. And then sub in the values for g and 4 pi squared. Eventually, you'll be able to get the value of big M as 1.01 times 10 power 26 kg. Okay. Right. So that is one part. Okay. Now, there is also another different method to do this, because sometimes some people don't like to find gradient. By default, I always find from gradient. But there's also another different method of doing this, which some people find easier. That one is using single point substitution. What I mean by that is this. Now you see, just now you already found x cubed is gm over 4 pi square equals to gm over 4 pi square t square, right? So this one you have straight line through origin, right? Now, if it's a straight line through origin, if you see that your equation gives you a straight line through origin, single point substitution to find answer is acceptable. Okay. What I mean by that is that, for example, rather than me using gradient to find the value of M now, what if I just find one value from the graph rather than 2 values on the graph? Say, for example, I try to use this point where I know that this one would have a value of 0.1 and 1.3. Let's just say I use this point where this one was supposed to be my t square. Sorry, maybe I use a different color. Where this one is supposed to be my t square and this one is supposed to be my x cube, right? So what if I just read from one point, get the value for one point, and then substitute it over here, substitute for x cubed, substitute for t square, substitute for m and 4 pi square, sorry, substitute for x cubed, t square, g and 4 pi square, and then eventually find out what's the value of m. If you want to do this by using just one value from a point, it is acceptable. Okay. All right, but usually this one is only good if you know the equation gives you a straight line through origin. Okay. If it's the equation that gives you a straight line through origin, you want to find the answer, you can actually just read off from one single point and sub it inside. All right. Some people find this to be easier because you only need to do one reading and one calculation. Then some people find gradient calculation to be a bit tedious because you need to find 2 different points. You need to do the calculation a bit more. Okay, so up to you lah. All right, but what I'll just mention is that single point substitution more often than not is only for straight line through origin. If your equation gives you a straight line through origin and you want to find some value out of it, just read one point, that one is okay. All right. Here, the question actually mentioned, the marking scale actually mentioned one other thing. This one, they mentioned that if you're calculating the answer from a single point solution here, You need to specifically show a line that has been shown extrapolated through the origin. Okay, this is the examiner's comment for this question. If you're trying to find just for a single point the answer, make sure that you show the line is extrapolated to the origin. Okay, because as I mentioned to you just now, single point substitution more often than not is only applicable for straight line through origin only. Okay, all right. Okay, page 10 doesn't seem to be the start of the question. It's supposed to be page 9, sorry. All right, so have a look at page 9. This is March 16, P42. Okay, so the first question is talking about state Newton's law of gravitational attraction. This is something that we just learned last week. We can actually just copy back whatever we learned from the notes, where we say that force between 2 point masses is proportional or directly proportional to the product of their masses and inversely proportional to the square of the separation. You just really need to say this portion only. Okay, the rest of it I think is a bit extra. You don't really need to write them if you feel that it's too long to write. Just make sure you say force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation. Mentioning point mass is 1 mark. Mentioning proportional to product of mass and inversely proportional to square of separation is your other mark. Okay, so this one should be quite straightforward. Okay, now have a look at part B. B says that you have a satellite of mass small m that has a circular orbit of radius r about a planet of mass big M. It may be assumed that the planet and the satellite are uniform spheres that are isolated in space. Show that the linear speed v of the satellite is given by this expression over here, where g is the gravitational constant. Explain your working. So here, they already specifically mentioned to you that you have a satellite that is in orbit around a planet whose mass is big M. So the satellite itself has a mass of small m. So it's in circular orbit like this. I want you to show that the linear speed of that satellite, which is tangent to the point which you're considering, is given by this equation here. V is square root gm over r. So this one is actually relating to page 6 of your notes, okay? The one where we talk about satellite orbits from last week. Okay, so we talked about this last week for satellite orbits. If you want to find out the linear speed, there's a particular derivation or equation that you need to know. So here they mentioned to you that you need to explain your working. Now, in the first place, since this satellite was moving in circular motion, because it's in circular orbit, so since it's circular orbit, it must be moving in a circle. So if you are moving in a circle, you must have what we call centripetal force. You need to have centripetal force in order for you to move in a circle. In your case, the centripetal force actually came from the gravitational force of attraction between the satellite and the planet itself. Okay, so the thing was that centripetal force is a kind of resultant force. It needs to be provided by some other existing force. All right. Now, when they say explain your working, I mentioned before. Yeah, when they say explain your working, I'm not sure whether I mentioned this before. For gravitational field questions, whenever you see mention of explain your working, it always refers to you having to write this statement. Okay, gravitational force provides the centripetal force. Gravitational force is the centripetal force. This one is the B1 mark, meaning to say that point must be specifically written in your answer. If you don't write that in, you will not get your mark. Okay, because this is a B1 mark. The point must be specifically shown inside your workings. All right. Now, one odd thing that the marking scheme mentioned was that you should not actually say that gravitational force equals centripetal force. This is the weird thing that the marking scheme actually mentioned, or rather it's the examiner's report. If you say gravitational force equals centripetal force, they don't accept that. Because according to them, they say this one implies equilibrium. centripetal force is one force, gravitational force is another force. So both of them are acting equal and opposite to another. That is what it was implying. So as best as possible, don't write equals to. Either just write provides the centripetal force or is the centripetal force. All right. Now then from here, you just proceed with what you learn of. Gravitational force is centripetal force, where you learn that gravitational force is gmm over r squared, and then centripetal force is either mr omega squared or mv squared over r. But because we're dealing with linear speed, we want to use this one here. Okay. So you will get gmm over r squared equals to mv squared over r. So just minus off whatever is not unnecessary. Eventually, you will get v equals to square root gm over r. Okay, right? So that one is fine. Then after that, you look at part C. Part C, they tell you that right now, let me just erase the things. Okay, part C, they're telling you right now that there are two moons, A and B, that have circular orbits about a planet as illustrated. Okay, moon A has an orbital radius RA of some value, linear speed VA, and orbital period TA. And then moon B has orbital radius RB of some value, linear speed VB, and orbital period TB. Okay, so the main thing is that they are in circular orbit, moving in a circle around the planet. So in our case here, you are asked to determine the ratios of VA to VB. What is the ratio of the speeds of A to B? Now, a lot of times when you do your paper 4, you will notice that subsequent questions tend to relate back to whatever you have done before. So like in your case, they suddenly told you that VA, they want the ratio of VA to VB. The hint would come from what you did previously. Previously, they already asked you to derive V equals to square root GM over R. So you ought to use whatever you have done before to try and solve the question. Okay, this is usually the pattern you will see. Subsequent questions in your P4 tend to relate back to whatever you have done before. All right, but not always lah. It's just that most of the time it's like that. So if you want to find out the ratio of VA to VB, you can actually just do something like this. You see, if I say that this one was moon A, and then I also have moon B, which is this one. This moon B was also moving in. Sorry, I didn't draw this one properly, right? This is moon B. Moon B was also moving in circular orbit about that planet that they're talking about. Okay, so moon A itself would have VA, moon B itself would have VB. Okay, the equation V equals to square root GM over R applies to B, it also applies to A. Okay, so when you want to find the ratio of two quantities, almost always you need to find a common equation that links both of them. In your case, it is P equals to square root GM over R. Okay, then from there you try to work out what is actually common for both cases, for both A and B. If you look at V equals to square root GM over R, the thing that's common for A and B was that your mass that you're orbiting about is the same. You're orbiting about the same planet, so the big M is the same. And then gravitational constant is a constant, so that one is actually nothing to consider. It will be the same for everything, for both cases. So G and M are constant, you get V is inversely proportional to 1 over square root R. Then all you just need to do is do what you usually do in maths. VA to VB is RB to RA square root. Because here, VA to VB is 1 over square root RA, 1 over square root RB. So eventually you will get square root RB to RA, which is what you're seeing here. Right, so just submit your values and eventually you will get your answer. All right, remember to square your values. You already have the radius from the previous page. All right, so get the ratio, square root it, and you will get the ratio as 13. All right, okay, so this part is okay, pretty straightforward. Now, if you look at the next part of the question, this time they're asking you what is the ratio of periods of TA to TB. Okay, ratio of the period of TA to TB. Now, this one, you can also think of it as, yeah, it probably would relate back to whatever you have calculated here. Okay, but in the first place, what equation should you use? Now, if you recall what you learned in circular motion, there was an equation that related velocity and period together. If you remember, look at the first page of circular motion last time, I mentioned to you that omega is 2 pi over t, and then v is 2 pi r over t. So this equation here relates linear speed and period. So you want to use this, okay? So for my case, I know that v equals to 2 pi r over t can be applied to A. It can also be applied to B. For these two cases, this is the common equation that links them. But again, what is the constant here? You can actually just say that in your case, pi is constant, therefore V is proportional to R over T. Okay. Right, what I have here is actually just some sort of derivation to show that it was this. You actually don't need to do something like this. You can just say straight away say that V is 2 pi R over T. So 2 pi is constant, V is proportional to R over T. And then because you want T now, T is proportional to R over V instead. Okay. Then after that, we want TA to TB, right? TA to TB would be RA to VB, sorry, VA, RB to VB, which gets you this. Okay. So the ratio of the radii, you can find from your previous page. 1.3 times 10 power 8 divided by 2.2 times 10 power 10. And then the ratio of VB to VA is 1 over 13. So be careful about the ratio. VA to VB is 13. But VB to VA is 1 over 13. Okay, the ratios are in a different order. So your final answer, you will get 4.55 times 10 power minus 4. There's no units, all right, because the units cancel off. Now, the last part here has something to do with your stationary satellites. The planet spins about its own axis with an angular speed of 1.7 times 10 power minus 4 radians per second. Okay. Moon A is always above the same point on the planet's surface. Wait, let me just erase off some of this unnecessary stuff. Okay. Planet spins about its own axis with this angular speed. Then they specifically told you that Moon A is always above the same point on the planet's surface. So the moment you see that they say it's always above the same point on the planet's surface, this one is really telling you that you are having a geostationary satellite. Okay, which in turn will tell you that the omega, the angular speed of your satellite, must be the same as the angular speed of your planet. Okay, must be the same as the angular speed of your planet. All right. Then from here, they suddenly say determine the orbital period TB of Moon B. So here they tell you moon A, then suddenly they ask you for moon B. All right, seems to be a bit odd, right? Now there's a reason why you have period for moon B here. You can actually find out period for moon A first, and then subsequently find out the period for moon B, because you see in the previous part of your question, notice that you already found the ratio of TA to TB, and you say that TA to TB is 4.55 times 10 power minus 4. Okay, so you can find TA, you can find TB, because you already know the ratio here. All right, so that's what you want to do right now. So this is your planet, and then this is moon A. It orbits like this, no? Okay, right. So one of the things you can do is that you use back the equation omega equals to 2 pi over t. This one is for moon A, all right? This one I'm talking about for moon A. I apply omega equals to 2 pi over t for moon A. I already know the omega for this. Oh, sorry. I call this geostationary satellite line. Yeah, it's correct now. It's a natural satellite. Nothing wrong with the term. Okay, so I apply omega equals to 2 pi over t for moon A. I know that the angular speed of the moon or the natural satellite is going to be the same as the angular speed of the planet. So this one, as I mentioned, it will be 1.7 times 10 power minus 4 radians per second. Okay, so I already know the omega. So here in my case, t is 2 pi over omega, TA is 2 pi over omega A. So 2 pi over 1.7 times 10 power minus 4 will give me 3.696 times 10 power 4 seconds. All right. And then given that I know the ratio of TA to TB being 4.55 times 10 power minus 4, I just sub in the value for TA. I'll be able to find out the value for TB. It will be 3.696 times 10 power 4 divided by 4.55 times 10 power minus 4, eventually giving you 8.12 times 10 power 7 seconds. All right. Have a look at page 21. This one is June 17 P42. Right, we are looking at that. Okay, so June 17 P42 will get us this. Right, now define gravitational field strength. All right. Gravitational field strength G is just simply force per unit mass. That's all there is to it. Okay. Now, the mass of a spherical comet of radius 3.6 km is approximately 1 times 10 power 13 kg. Assuming that the comet has constant density, calculate the gravitational field strength on the surface of the comet. Okay, so they told you that your comet is spherical, so its cross-sectional area ought to be a circle. All right. So you know that it has a radius of 3.6 kilometer, and they want you to find out what is the gravitational field strength on the surface of the comet. So this one, they want to find out what is the G. Now, when it comes to your gravitational field strength, you've learned from your notes that you can either have two equations. Either it's Fg over m, or either it is Gm over r squared. Now, you would normally only use the first one here only if a test mass is available. Okay, only if a test mass is available. If you don't have a test mass available, you normally would not use this equation. All right, so in your question here, your comet, you want to find out the gravitational field strength on the surface, but there's no test mass given. They didn't tell you I put a mass there and I found out that the gravitational force acting on it was this. If you had, say, a test mass here, and you know the value of the gravitational force acting on it, you could have used equation 1. But the fact is that you don't have. Okay, so since you don't have that, you are most likely going to be using equation 2. Right? Since you already know the mass in the first place and the distance to consider. They already told you your mass is this one. Okay, so your mass is 1 times 10 power 13 kg. Your distance is 3.6 kilometer. So you just use your values. G is gm over r square. You get 6.67 times 10 power minus 11 times 1 times 10 power 13 divided by 3.6 kilometer. Remember to change back to meter and remember to square. Now, one of the common problems with gravitational field that most people always do is that they always forget to square or cube their equation. They remember to change their units, but then after that they forgot to square or cube. So be very careful about the questions, all right? Now, eventually your G will be 5.15 times 10 power 5 Newton per kg. All right, so this one is pretty straightforward. Okay, then you look at the subsequent part of your question. A probe has a weight of 960 Newton on Earth, lands on the comet. Using your answer in 1, determine the weight of the probe on the surface of the comet. So right now, they told you that you actually have a probe that is landing on the surface of the comet. They want you to find out the weight of that comet. Sorry, the weight of that probe. So let's just say that your probe has a mass of small m. This is your probe. They want you to find out what is the gravitational force. So again, here, if you want to find the gravitational force, you could have just easily used Fg equals to mg. This one you can apply over here. You know that your test mass is your probe right now, and you know your gravitational field strength at that on the surface. So you can actually apply that equation. But then you have a problem. You do not know what is the mass in the first place of the probe. Now, this one actually kind of relates to what you learn in your AS. In AS, remember we told you this weight or gravitational force varies with location. Okay, wait now, sorry, my pen is acting up. Okay, in your AS, we told you that weight or gravitational force varies with location. If you have an object on Earth, it will weigh a certain value. But then when you put it on the moon, it will weigh a different value. If you put it on Mars, it will also weigh a different value, right? But then what we told you was that although weight or gravitational force varies with location, mass remains constant regardless of location. Okay, so here you need to find out the mass first by using the information you have when it was on Earth. On Earth, you know the weight is 960 Newton. You use W equals to mg. 960 equals to m times 9.81. Mass is 97.86 kg. So from here, you can then find out what is your weight on the comet. It will be the mass of the probe multiplied with your gravitational field strength on the surface of the comet. You get 97.86 times with 5.15 times 10 power minus 5, giving you 5.04 times 10 power minus 3 Newton. Okay? So this one would be for this question. Okay, so this one should be okay. It's a pretty straightforward question. Okay, the other one would be part C. Part C is more on testing your knowledge of field lines. So let me clear off the drawing. Now, in part C, they told you that a second comet has a length of approximately 4.5 kilometer and a width of approximately 2.6 kilometer. The outline is illustrated in the figure below here. Suggests a similarity and a difference between the gravitational fields at the surface of this comet and at the surface of the comet in B. Now, just now the comet in B, which was the previous question, it is actually a spherical comet. It has a circular cross-sectional area. And then we mentioned that the radius is 3.6 kilometer, if I'm not mistaken. Isn't it? Yeah, it's 3.6 kilometer. Okay, then after that, you now have a second comet, but this comet looks weird. It has a irregular shape. It doesn't have a uniform shape, okay? The comet in B has a uniform shape, but the comet in C has an irregular shape. It's a non-uniform shape. They want you to compare the similarity and difference between the gravitational fields on the surface of both comets. So before I move to that, let me just go and mark out certain things. Your length is 4.5 kilometer. Your width is about 2.6 kilometer. Okay, right? Okay, now, if you want to evaluate the difference in the gravitational fields, you can try and draw out the field lines around both shapes. For the uniform shape, the circular comet, the circular comet, you can try to draw the pattern. You already know from last week that it should be radial. The reason why it was radial in the first place was because you need to maintain 90 degrees with your contacting surface. Okay. Now, for the case of the irregularly shaped comet, the non-uniform shaped comet, you can also try to draw the field lines, but then you see your field lines will look really, really weird. So you first try to draw your field lines at 90 degrees to each other, at 90 degrees to your contacting surface. If you try to draw them at 90 degrees to your contacting surface, they will probably look like this. Okay. Because you're still trying to maintain 90 degrees, you see, with your surface, it could probably look like this now. Okay, I'm just trying to extrapolate everything out. Okay, now I just try and do everything out. I'll just draw simply first. Now, one thing I should mention to you is this. When you're drawing field lines, let's just say I look at this point and I look at this point, they must maintain 90 degrees, right? So if I try to draw the field lines and both maintain 90 degrees, it will seemingly seem that the field lines will intersect across each other. Now, actually, when you're drawing field lines, you're not supposed to have field lines crossing with each other. This is actually another rule of field lines. If you look back at the first page of your notes for gravitational field, I told you 3 things about field lines. Field lines must always be perpendicular to your contacting surfaces. Spacing of field lines is a measure of your field strength. The closer the spacing, the stronger the field. And then I told you field lines must always point inwards. There was also another thing that I didn't really mention because it was never really tested inside your exam. This one could be part D if you wanted to write it down. This one, field lines cannot cross each other. Okay, let me just write this one out. Field lines cannot cross each other. Okay, they cannot cross each other. When you're drawing field lines, they should never be shown as crossing each other. Okay, so in your case here, you'll notice that I try not to cross the lines, right? So the actual way of drawing the field lines is to ensure that they don't cross each other. Just draw something simply, all right? You don't need to draw so many lines, just draw some lines would do that. Okay, so the main thing is that when you draw a few lines, you must still maintain 90 degrees at all times. So because your few lines is trying to maintain 90 degrees with the surface of your comet right now, your pattern looks kind of weird, all right? So that is one thing to note here, all right? Now, in terms of the direction of your field lines, for the spherical comet, the field lines would always be directed inwards because it follows the direction of force acting on the test mass placed at that particular point. Okay. Now, for the irregularly shaped comet, it will be the same thing also. It will be directed inwards. Okay. Now, what is the similarity between both comets in terms of the field? You will say that the field is actually directed towards the comet for both cases. Okay, field lines will always be inwards for gravitational field. Okay, field lines is always inward for gravitational field. Okay, so this is one similarity. And then what is the difference between those two? The difference between those two is that field lines for B was radial, and then for C is non-radial. Okay, this is actually comet B. This is actually comet C. Okay, now then after that, there were some other questions that, sorry, there are some other answers that the marking scheme gave. All right, so I'll go through that also with you. Now, if you look at similarity, you could also say that rather than the field line is being directed towards the comet for both cases, you can also just say that both gravitational fields are attractive. They will cause a mass to be attracted towards them. Okay, this is also fine. Now, if you look at the other answer, they told you that field strength is the same order of magnitude. Okay, look at the wordings. Field strength is the same order of magnitude. They're not saying they are of the same magnitude, but rather they're saying they're of the same order of magnitude. Now, what do we mean by same order of magnitude first in the first place? It relates to this. Let me just try to write out for you a few values. If, say, for example, I give you 25, 2,000, 250, 2,500, and then maybe I should do it one by one. 2,500, 25,000. Now, if you look at this one, these values here, and I ask you to compare the values, 25 is obviously not comparable to 250. 250 is obviously not comparable to 2,500. 2,500 is obviously not comparable to 25,000, right? I mean, in your mind, this one, they, in terms of how large they are, they're not even the same. It can't be compared. All right, that is what order of magnitude actually is. Now, to give you a better idea of what order of magnitude is, you can just think of it as this. If I try to write them in scientific notations, 25 will be 2.5 times 10. 250 will be 2.5 times 10 power 2. 2,500 will be 2.5 times 10 power 3. And 25,000 will be 2.5 times 10 power 4. Okay. So when you want to look at order of magnitude, you normally look at the power of tens. Okay, this one here just now I mentioned to you, this one is not same order of magnitude. Okay, this one, these values that I give you here are not having the same order of magnitude because you see the power of tens are different. Okay, this one is different power of 10 POT. Okay, let me just erase this one. This one is different power of 10. Okay, if you see that you have different power of tens, we normally do not call them as same order of magnitude. We will say them as different order of magnitude. Now, if you have same order of magnitude, it's something like this. Let me just write this out. If you have same order of magnitude, it could be something like this, where I tell you you have maybe 3,200, 2,800, 5,700, and then maybe, for example, you have 6,200. Okay, these are what we call same order of magnitudes, right? Because you can see here, this one is 3.2 times 10 power 3. This is 2.8 times 10 power 3. 5.7 times 10 power 3, and then this one 6.2 times 10 power 3. Same order of magnitude here kind of refers to the fact that they have same power of 10. And this is what we call same power. This is what we would say as same order of magnitude. Okay? Right, but for both of these cases, obviously this one will be considered as different magnitude different magnitude or values. Okay, both of these set of values are considered to be different magnitude, different values, right? None of them are the same. Okay, but but there are some similarities that you can see for the different sets. Okay, for the second set is same order of magnitude. For the first set, not same order of magnitude. Okay, that is what order of magnitude means. All right, now going back to the question, they told you that field strength is the same order of magnitude. It's kind of referring to this. Okay, maybe I should use a different color. It's getting really messy. Same order of magnitude kind of refers to this. Okay, it could be that this G here on the surface is maybe 4.2 times 10 power 2 Newton per kg, for example. And then for your planet here, your G is maybe 5.6 times 10 power 2 Newton per kg. Okay, the values are different, but they are considered same order of magnitude. Okay, now in the first place, why would I say that they are same order of magnitude in the first place? Now this one you have to look at the size of your comet. If you look at the size of your comet, this one is about 7.2 kilometer diameter in terms of the diameter. And then this one here was 4.5 kilometer. Okay, size-wise, they are the same. All right. So what I will just mention here is this. Both comets have approximately same size. Therefore, their mass is about the same. Both comets have approximately same size. Their mass is about it's comparable to each other. What this is. Okay, both comets have approximately same size. The mass is comparable to each other. Therefore, their G is same order of magnitude. Okay, the comets have about same size. Their masses obviously will be comparable to each other then, so their G will be same order of magnitude. Okay, unless you're saying that one of the comet is so much larger than the other, their mass will be different, the G would definitely be different. It won't be in the same order of magnitude. Okay, right? So that's what field strength being same order of magnitude here means. Okay, now then after that, if you look at the differences part, the statement in red that is from the marking scheme also, they told you that field strength is the same over the surface of the comet for B, but varies over the surface of the comet for C. Okay, now here they are telling you specifically that for B, the uniform shaped comet, the field strength is actually the same over the surface, throughout the surface. When they say the surface, they're actually referring to something like this. Wait, let me just highlight it for you. They're really just looking at this small portion over the surface. They're not considering a very large distance like this. They're considering only a very small distance, okay, over the surface. Okay, so now if you just look at the regularly shaped comet, the uniform comet, throughout the surface only, what can you say about the spacing of the lines from one to another? You see, if you look at the spacing of the lines from one to another along the surface, you will see that the line spacing is constant. Therefore, G is constant. This one is you're talking about along the surface. You are not considering some far distance away from the surface. You're just considering along the surface. Okay? That's why here we can say the field strength is the same. Now, the part where for the other comment, they say that field strength actually varies. This one you can actually see this quite clearly from your diagram. Let me just erase all certain things now. Otherwise it's getting really messy. If you just look, for example, the lines, say for example, I'm looking over this surface only. All right. What can you say about the line spacing? See, this one is like this one is like this, like this, like this, like this, like this, and then like this, right? I mean, if I ask you, can you say that the line spacing is going to be the same throughout the surface? You cannot say so, right? Because the surface is, I mean, the comet is irregularly shaped in the first place. The line spacing you can see are not going to be the same throughout. So this one here will be the direct opposite of what I just wrote here. Look. So here, this one, I'll just say that line spacing varies. Therefore, G varies. Okay. That's what this answer means. Okay. Right. So that's for that part. Yeah. Okay. So the comments in red takes a bit of understanding. It'll be easier to just take the comments that are written in pencil. But those two are actually the easiest to understand. Okay.